Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this time we have together, Lord. And I pray. Amen. So yeah, as I've mentioned to some of you guys, I'm wearing this shirt because my son Isaac asked me to. And it's in celebration of his 7th birthday. That's at least one interpretation of me wearing the shirt. So, I'll stick with that. Lies. It may have been also in part due to a conversation with a student in here, and some kind of enabling. What's the word? All right, let's get rid of this here. All right, so the goal in this paper, of course, is to study differential equations over an algebra. And so it rests upon the development that we've already talked about, differentiation, power series, all that. And we just get straight to it. So we've talked about this representation stuff before, I think. We've learned things about submultiplicative norm this semester already, right? None of those things are in this paper because we just learned those recently. I still haven't talked to you guys about D2 versus D1 differentiability, and maybe we'll get around to that someday, but I always study differentiability with respect to the Fréchet quotient. Basically, I'm assuming that the function is such that the differential is in the regular representation of the algebra. For me, that's what a differentiable means at a point. And of course, that's conveniently captured by the Cauchy-Riemann equations, which are elegantly stated at the algebra level as that. Goodness gracious, I should have put my glasses on today. Oopsie. So, getting along here to the point, eventually, we have calculus. We have, derivative of the sum and sum of the derivatives. We can pull constants out. For commutative algebra, we have the product rule. We have the chain rule, and we even have power rule in the appropriate contexts. Yeah. There are really, really beautiful results for higher derivatives, as I've mentioned before. In particular, if we calculate the mixed partial derivative, mixed kth partial derivative of f, and f is a differentiable, then we can convert that partial differentiation into an algebra multiplication, like so, assuming that the identity for the algebra is paired with the first coordinate in the coordinate system. All right, sorry, it's all old news for you guys. That gives me a license, of course, to convert, differential equations into algebraic equations into differential equations, really, right? Okay, so here's the first major result in this paper, I think. I assume A is a commutative algebra throughout the section. I'm going to look at functions from AM, like M tuples of the algebra, to K tuples of the algebra. So my variable, G vector, well, the components of G will be G1 through GK. Each one of those is a differentiable. That's what I mean here by a differentiable in that context, okay? So, anyway, so each component function is a differentiable in the sense that it's real. That G vector is real differentiable, and in fact has a linear differential. I think maybe that should be G sub I here. Sorry about that. That's supposed to be a G sub I. Oh, I'll be hearing from my referees. Oh, most unfortunate typo right there. Stink. It turns out, though, that G vector is also going to be real differentiable with a right linear different. I mean, that turns out to be true, but that's a derived consequence of right differentiability of the component functions, which I've derived down here somewhere. Okay, anyway, each component function is a differentiable. So suppose we have AM, the domain, right, has algebra variables Z1 through Zm. And so this is a differentiable at P. We define partial G partial Zi to be the directional derivative in the Frechet sense of the function at EI. So that's the directional derivative in the Frechet sense is given to exist. So this is something I can define, and indeed it would also coincide with our usual definition of A differentiability, right? It's usually the case that we define df dz to be the the partial derivative in the first coordinate direction, right? So this is a good candidate for that meaning. But it's EI, all right? So here you don't just have E1, you've got E1, E2, and so forth. So anyway, so generally speaking, the directional derivative, the differential of G at this tuple H1 through HM, it's going to be equal to H1 partial G partial Z1 and so forth and so on. This is just advanced calculus. And then, but I need this setup. I need these kinds of partial derivatives with respect to a bunch of algebra variables to make sense of what follows, okay? So I haven't really studied them on their own so much. I mean, there's probably other neat theorems you could say about the calculus of several algebra variables that I haven't, talked about, but my goal here is really just to prove this theorem. So let I be compact and star-shaped. What's that mean? So A is Rn, right? Up to some notation. Basically, it's an n-dimensional real vector space. And so compact means closed and bounded in this context, right? And star-shaped means that you can pick a star center for the shape, such that any point in I can be reached from a line segment, right? Then I let R be the Cartesian product of I with, what is that? AK? Let me try to make it a little bit bigger here for the sake of my reading. Maybe you're reading too. So this is the Cartesian product of that. I think that's the unit interval. That's like 0 to 1. And this is just k-tuples of algebra elements. And so suppose we have a function that goes from this R, the Cartesian product of the unit interval with the k-tuples of A, to AK. Suppose that's a differentiable. And suppose further that the partial derivative of f with respect to y, son of a gun. Oh, right. I'm sorry. The partial derivative of that with respect to yi is bounded by L for each z comma y in there. So now I'm using y for the variables that are attached to the, let's see here, the a sub k piece, and z is in I. Now I is not the unit interval. I'm wrong. I is the compact star-shaped thing in A. Excuse me. I should not have said that I is the unit interval. That is not what I mean by I at all. So sorry about that. Duh. If I could read my own typing, Anyway, so we pick a point in here, right? All right. Well, that's kind of it's like a verse in scripture you'd like to memorize, right? So like there, done. Right? Short. The initial value problem, initial value problem, dy dz is equal to f of zy with that initial condition has a unique solution on I. So this is kind of an analog of the theorem we see in calculus, in differential equations, where if you have a differential equation dy dx equals to f of xy, if the partial derivative with respect to y is what? If it's non-zero at the point, then there's some neighborhood of that point where there exists a unique solution, right? So I think usually there's also continuity attached there. So if it's non-zero at one point, it's got to be non-zero near the point, right? Which, well, anyway, this is somehow it's not exactly that one, but it's kind of in the neighborhood of that theorem. Well, anyway, this is the theorem I'm trying to prove. So if the partial derivative of this defining differential equation, the f which defines the differential equation, is bounded for each for each z is stuck in I, and the y is free to range over the whole algebra. You know, well, it's a k-tuple in the algebra variable. All right. So the basic idea here, and you guys probably have never seen the proof of the. I doubt you've ever seen the real proof, right? Do you remember from differential equations where we proved the existence and uniqueness theorem? Yeah, I didn't remember either. But Nagel, Saff, and Snyder, which is a great book, they have an appendix on existence and uniqueness, and in that appendix they give the proof of that, the sort of analogous theorem to this in the real case, right? In terms of what's called a Picard iteration, and it involves the contraction mapping and some pretty standard analytical techniques, and I was able to adapt that to the current context as follows. So first of all, we build the initial. So my initial iterate is just that y sub naught is equal to w naught, right? And then for higher n, I define the n plus 1th iterate to be equal to, well, the initial w naught plus the integral. This is the algebra integral, right over the algebra, from z naught to z of f star d zeta. Now, that makes sense here. Why? So I have to fess up to what I mean by this, all right? Because you might, if you're, honestly, did I define that yet? I did not. My bad. So, but I do shortly thereafter explain what on earth I mean by this expression, right? So here, of course, that's the line segment from z naught to z. We know how to build that. That's just the parameterization from z to z naught. And you know that has to be fall inside I because I is star-shaped, all right? So we're integrating along that path. Yeah. Star-shaped means that I has to look something like, I don't know, something like that, where there's some kind of star center. So any point that you get to in the shape, you can get to from a line segment from something called the star center. There's a star center. Like, not every point has to be a star center, right? It can be star-shaped, and not every point is reached. Like, this would not be a star center, right? Because, yeah, I can reach these points, and these points, and these points, these points, these points, right? But that would not be a star center because, of course, I can't reach up here, and I can't reach down there. But it's star-shaped if there exists a star center, which means that any point in the shape can be reached by a line segment.
Are we about to find out in this thing right here why it needs to be that structure?
What's that?
Are we about to find out, like, in this piece why it needs to be that structure?
Oh, I need that in order to make this integral make sense. Because otherwise, when I set up the line segment z naught to z, see, if I choose z naught being a star center, did I say z naught's a star center? I should have said z naught's a star center. I'm sorry, I made the referee work too hard on this, I'm afraid. Well, yeah, I mean, star shape does imply path connected, but it's stronger than that. Yeah. Excuse me. So, I think I'm missing a very important little tidbit here. Let z naught be a star center. Maybe I'll get around to saying it here shortly. But anyway, if z naught's a star center, then this, by definition of star-shaped, is a subset of I. Which means that zeta, right? This zeta is at least ranging over the places where we've defined f, and we're also where we know f's derivatives are bounded. But what I actually mean by this, since f is actually vector valued, is I really mean it's a vector of integrals in the sense that I describe in the first paper that we talked about. So introduction to calculus. I mean, this is so this is like if we integrate a path, we integrate each component one at a time. And usually that kind of path integral will just be doing an integral over time. All right, so like zeta is playing the role of time here. It's sort of like a path, but instead of the independent variable being time, the independent variable is an algebra variable, which I'm calling zeta, if you want to guide your intuition here. But this, I'm actually this is actually definition we define. This means that. And again, these are all well defined because these line segments are inside I, over which we are given that f is defined. And more than that, we know that f is bounded in a certain way. But in addition, I can look at this, right? If I look at y naught plus the sum of these differences, what happens? Y naught plus y1 minus y naught plus y2 minus y1. Well, you see what happens. Jump, 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 jump. It telescopes down. So this sum plus that data point is actually just yn, right? So what does this tell us? So what that means then is the uniform convergence of this will provide uniform convergence of that. So if I can find, if for every n greater than for each epsilon greater than 0, I can pick I can go far enough out in the sequence to make it small for every point in the domain, uniform convergence, right? Well, if I have uniform convergence of this, and of course this is a constant plus that, so uniform convergence of this means uniform convergence of the sum. That will imply uniform convergence of that. But uniform convergence of this is very nice because it's a series, which means we can use the Weierstrass m-test. If we can dominate it, if we can majorize it with a series, a numerical series which converges for each possible input to these, then it follows that this is uniformly convergent, and hence that's uniformly convergent. So that's again, this is a standard part of the argument in the usual case, actually. All right, so moving forward. If I is compact, then that means that we can bound f like that, right? I mean, if f is continuous and we're looking at a compact set, then the extreme value theorem says we can find a bound. So I mean the norm of f of zeta, comma. So here the variable here is zeta. Zeta is being taken from a compact set. W naught is fixed. W naught is a fixed thing in AK, which is by no means compact. But on the other hand, there is no W naught dependency. W naught's fixed throughout this discussion, and it's part of the initial data, right? So it's not varying. And yeah, so that by continuity in the extreme value theorem, there exists an M. So for Z naught being this line segment inside the I, we have that the norm of that minus that is what? How'd that happen? Well, that goes back to how I defined the y sub 1. Remember, y sub naught was W naught. Y sub 1 was W naught plus the integral over the line segment of f. So when you take that difference, that minus that, you cancel out the W naught piece, and what you're left with is just the integral of f of zeta evaluated at W naught over d zeta, like so. But then this, remember, is bounded by m and by the Mammal theorem. I mean the submultiplicative estimation of integration theorem. We have the bound for the function and then the submultiplicative constant of the algebra. And then this, why that? Isn't this supposed to be the arc length? What is the length of this arc? It's a line segment, right? So the length of the arc is the displacement vector's length from z to z naught. Then to make further progress, you have to consult something deeper. In particular, I had to take a look in Zorich mathematical analysis too, and look up the generalization of the mean value theorem for our current context. Did you guys know there is no mean value theorem for functions of several variables? In the most naive way you could think of. So think about this, a helix, right? Here's a helix, right? We start here, we go around, whee! We go back up, and that was supposed to be over the same point here, over the same point. All right, there we go. And it keeps going. So compare this point and this point. R of T naught, R of T1, right? So what's the R of T1 minus R of T naught? See, the most natural generalization for the mean value theorem for functions of several variables would be that this is equal, this is the average velocity, right? It should be equal to the instantaneous, you know, the RDT for what? For some T star, right? Where T star was between these two guys, right? Right, there is, exactly, the average rate of change is straight up vertical, and there is no purely vertical velocity vector. So you can see that the naive generalization of the mean value theorem to space to paths is just not true. So what takes its place is there is something that's true, but it involves something a little more subtle. And that's what I needed for lemma 3.2. What you can say is that you can say something like this, basically. R of T1 minus R of T naught, all right? The norm of that is less than or equal to M times, you know, delta T. It's I'll put some quotes on that. It's a little bit more sophisticated than that. It involves taking the supremum over the appropriate this and that, but it's kind of a bounding result instead of a. They're actually that the instantaneous is. You can't say that the instantaneous rate of change is actually in its suitable generalization attained. It matches the average. It's just not the case. But you can still say something about bounding, and that's what we need here actually. So with f and r, as in the preceding discussion, there exists an L greater than 0 such that, for which the f of zeta v minus f of zeta w is less than or equal to L times v minus w. So if we fix the zeta, right? If you fix zeta, the distance between this point and that point, the distance between this point and that point is exactly that. If we fix zeta, right? The distance is completely, like the change in distance between those two function inputs is completely governed by the vector part, if you will. Now, the reason that lemma is true is over here. So if we use df vector to denote the Fauché derivative for f from r to ak, then theorem 1 on page 73 of 12, this is Mathematical Analysis 2 by Zorich, I believe, which is just an amazing book. You should all read it if you want to learn deeper calculus. I can't recommend it enough. It's actually it's a translation. It was originally Russian, and Russians have been using it for a while, and only recently, somewhat recently, has it been translated into, English. And it reads pretty good. It translated well. Anyway, so this difference is less than or equal to h times the supremum. So you're looking, so basically you see what's going on here is the change in the function from a to a plus h is less than or equal to the distance from here to here, which is norm h, right? Times the supremum of the norm of the Fauché derivative along the thing. But here, for our context, the norm of that pair is given by that. And so if I pick this pair in R, and that denotes the operator norm defined, You see, this is the bad thing about this proof, is we're touching on all kinds of stuff you guys have not really studied that deeply yet. Everyone who's currently paying attention, at least. Let's see here. But it's okay. So this is the operator. It's like, how do you calculate the norm for an operator? You take the supremum of the norm of the output of the operator over the unit ball. This is the definition for the norm of an operator. Like, you just feed it all possible unit vectors and look at the supremum of all those. That's the norm of the operator. That's one way to define it anyway, and that's what I write here. Anyway, so the Fauché derivative of f at x of w, if I say this is equal to that, then the norm would be that. But let's see here. So now what am I doing? df. Now I think this is like a generic statement, and then I'm plugging in different y's into down here, I think, if I remember right. Let's see here. So the Fauché derivative of f at the point P with respect to w naught w. So I do partial f partial z. That's the first coordinate in f, right? That times the w naught, and then this is this, the variables. Then my variable z. Then there was variable y1 through yk. So that I have the w1 through wk with respect to the y is my notation. It goes back to the notational setup here at the start. And then let's see here. Fine. So then I specialize here, P not being any point, but a point in this from A to A plus H, subset of R, where again R is the I cross K tuples in A. And I want to look at H equals to 0, comma H, because I'm fixing the zeta and just changing the second part of it. So like the change in the first part of the Z, comma Y vector tuple is changing, not the Z is not, the zeta is not changing. My other lingo. Let's see here. Then, so the W naught up here, that's W naught, and that's 0, right? But the W1 would be H1, the W2 would be H2, and so forth, right? So this simplifies to just involving partial derivatives with respect to Y, right? Right, and then. But we assumed that the partial derivatives of the function with respect to y were bounded by L. All of them, right? And for each point in R, by the way, this line segment is in R, right? So that means we can bound every last one of these norms is bounded by L. And so when we look at that, less than or equal to blah, 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 blah. So what do I got here? I got an M sub A, I got an L. Why is there a K? Oh, because there's K things here, right? And I'm using the note, I'm noticing that each component of H is smaller than the norm of H collectively, right? So I can replace H1. H1 is smaller. Norm of the first component in H is smaller than norm H. Norm of the second component in H is smaller than norm H. So I have that same thing everywhere. I can factor out just norm of H vector. And, all right. So what that gives me then from 20, which I think was the initial statement from Zorich, I have that the difference of f of a plus h minus f of a was less than or equal to h k l m a k l m a. Am I supposed to have a little h here? I don't know. There may be supposed to be a little h, but I don't think they're different actually. The norm of big H and the norm of little h vector are the same here given my notation. Why did I say I was going to I said I was taking it easy today. What planet am I from? Why would I do this? I should have just told you guys to read this. I'm an idiot. But anyway, you know that already. You're here. So All right, so what is this? Zeta V, zeta W, and R. So I've got my A is zeta W, my A plus H is zeta V. So as you can see, H is 0, comma, that difference. And applying that to my calculation above, we get that this difference is less than or equal to that, which was the lemma. To summarize, we use the extended mean value theorem adapted to our context to derive that lemma. It's still all finite dimensional stuff, all right? This is all just an elaborate calculation happening in Rn, but there it is. So now we continue with the proof of theorem 3.1. I let that L be KLMA and inductively suppose that that's the case. So you want to see an example of a non-trivial induction? Here you go. Or maybe that's already the, maybe I don't even show the induction. Do I show the induction? Maybe I do. Let's see here. It's been a little while since I wrote this. So that's my induction claim, is that this difference is less than or equal to that, right? Now it's true for n equals to 1, because what would this be in n equals 1? N equals 1, that would be m, ma, the length of z minus z naught. Yeah, we did look at that before. We've already seen n equals 1 earlier. That was essentially just the definition of y naught and y1, and just taking the difference. There was really not much to that there. And the the mammal theorem for integral. Next step here. Take the difference. So now I'm going to look at yn plus 1 and yn, the difference there, right? So I am trying to prove the induction, right? I want to show that this is less than or equal to m L to the n, m sub a to the n plus 1, z minus z naught to the n plus 1 over n plus 1 factorial. That would be my target, right, for this guy. So that difference is essentially, by the definition of how I set up the recursive sequence, the difference of these integrals. So again, the W naughts cancel, and you're just left, if you go back, this is not complicated, the part I'm currently doing. If we just go back to how I defined the y's, come on. Right here. So this is my definition for yn plus 1, recursive. So basically, we integrate the previous one. So we're looking at like yn plus 1 minus yn, so the W naughts cancel, and we're left with the difference of f over zeta y of the previous one and y of the previous one, or something like that. We get, all right, let's go ahead. So that should not be a mysterious step, right? And then what did I do? I said, well, by the mammal theorem, that's less than or equal to, oh, I'm using the lemma, right? So the lemma said that I guess technically I'm using an unproved, well, natural, but maybe a slight gap here. Because I just jumped from the path integral to like, well, words. So I know that this difference, right, is bounded by L MLA, I think this is true, but I guess I could expand it and be more formal about that. All right, I'm gonna go on. So, what's this then? What's the length? What's this mean? So I'm really claiming a theorem here that I haven't actually shown in this paper, but I think would be pretty easy. Like, it's a pretty trivial theorem to prove, which states that if you're integrating over like one of these path valued things, is less than or equal to the norm of the path function integrated with respect to arc length along the path. I mean, this is an arc length. This is an arc length integral. But it's more than that because that would just be norm of this, right? But I don't have norm of this anymore. I actually traded this out for I used the lemma 3.2. Trying to think of where did my, why don't I have, where'd my F's go? You guys understand? Where'd the F go? Was that lemma 3.2? Have I already forgotten it? Oh, that was lemma 3.2. We traded F's for no F's, right? So F does, lemma 3.2, lemma 3.2 in fact does erase the F, doesn't it? Look at that. If I could just remember what we already did 3 minutes ago. So the norm of F of zeta V, F of zeta W, that difference is just less than or equal to L times that for the appropriate L. There exists an L. And I think the question is, well, anyway. So I'm really using lemma 3.2 to bound this norm to be less than or equal to that. And then I'm using a theorem, which I think is natural, but I guess I've technically not proved here that the norm of the path integral along the path is less than or equal to the integral, the norm of the vector being integrated component-wise over the arc, with respect to arc length. Words. Well, anyway, then this, by the induction hypothesis, right, is what? Less than or equal to m, L sub n minus 1, m sub a, that, right? And this is where I was, at one point, really kind of like scared. I was like, oh no, how on earth am I ever going to recover and get the induction proof here? But then it dawned on me, I can do this integral. This is, this is nothing more than the, what is this? We're looking at the path from z naught to z, right? This is zeta minus z naught. This is nothing more than s to the n for arc length. Right? I'm going from z naught to zeta. The length of that is the arc length from z naught to zeta. This is exactly s to the n. And that is a notation for ds, really. And this is just a constant, so you pull it out, and you have the integral, s to the n ds, which we can do. And that gives me a z minus z naught to the n plus 1 over n plus 1, which beautifully gives me my n plus 1 factorial and my L sub n rather than n minus 1, and my m sub a to the n plus 1, and of course my z minus z naught to the n plus 1. Induction complete. So, proof by picture. You want me to prove it? You mean write a picture?
I want you to draw a really big star and build a path.
It's here. So anyway, hence, I have this bound for the terms in my iterative defined functions by induction. And so if S denotes the distance from z naught to z, and I set beta equal to mesl, I mean m sub a SL, then we find the following bound. The difference between these guys is m over L beta to the n over n factorial. Okay. And since I is compact, I know there exists an S naught for which we can bound the distance from z to z naught by S naught, right? So I can let beta sub naught be mulso? No, m sub a LSO, and note that goodness gracious. Does this ever end? So that is beta is sub naught to the n over n factorial. This is a fixed but arbitrary constant, kind of depending on the size of our domain that we're looking at. And what happens is as n goes to infinity here, I mean, I think as n goes to infinity, well, I guess I can't say anything yet, but well, check this out though, right? So sum n equals 0 to infinity of beta sub naught to the n over n factorial. Well, that's e to the beta naught, right? This series definitely is a converging one, plain old garden variety exponential, and so that majorizes the this series, right? Not okay. I mean, technically I need to take that and multiply by m over l, which are fixed but arbitrary constants here, and then m over l times this will be a numerical series which majorizes this, consequently showing that in fact this guy right here is uniformly convergent, and hence by the argument earlier, this is actually converging uniformly to y star on I. Right. Now it still remains to show that y star is in fact a solution to the initial value problem. So if I have yn of z naught is equal to w naught, uniform convergence implies pointwise convergence, by the way. So y star of z naught, I can look at the limit as n goes, y star is the limit as n goes to infinity of y sub n, right? And so this is the pointwise convergence, I believe, right? Don't listen to me. I mean, anyway, this is something we can do as to the reason, and as what it actually is. I wouldn't trust myself today at this point. But anyway, I'm pretty certain about that step. And then this, by construction, is, what's that? Limit as n goes to infinity. Oh, the fact that yn of z naught is w naught is manifest from the definition of y naught. If you plug in, if you go back to where we defined y sub n, and you plug in z naught, the integral goes from z naught to z. If you put z equal to z naught, the integral is over the line integral from z naught to z naught. So the integral just leaves you with w naught for every iterate n. So the fact that every stage of the iteration sends z naught to w naught, that's built in, that's manifest from the definition of the y sub n from the start. So this is not a deep step. This is just a definition of yn step. And so there you go. That shows you that the limiting function actually also satisfies the initial condition. And to see it's a solution, well, let's see here. Y star was the limit as that goes to that, which, by the way, was the limit as n goes to infinity of here was the definition of y sub n. But the cool thing is, if, let's see here, what can I do next? Uniform convergence of the yn, all right? And the continuity of f imply uniform convergence of that. So I can exchange the order of integration and the limit. I can bring the limit inside to deduce that this plus that, which, by the way, is just to say that. So using the continuity of f and the uniform convergence of the y sub n, I can bring the limit inside like so. And that shows what? Now, this then goes to the, one of the last theorems in my first paper was on differentiating integral with variable bounds. If you differentiate an integral with variable bounds, well, guess what happens? You get back the integrand again with the variable bound in it, right? I mean, so like dd zeta of this is just f of zeta. And that would extend, I mean, I think I only proved it for a single variate integral last time, but that will extend, I mean, if you, I don't know if you ever thought about this or not, but if you were to do ddt, right, of the integral from t1 to t of something like r of t, well, let's say r of tau d tau, like this, if this was a path, integral of a path, then you different, I mean, it's not hard to see that that would still give you R of t. And the same thing is true for my algebra integral, because technically speaking, I've proved it for not a vector here, but for a function, an algebra valued function in the first paper. But here I'm really applying that theorem for a vector, for a path of integrals, which is more like this. But if you know it for one of the components, you can just string it along for each. Yeah. All right. Then, so the bottom line is if I differentiate that, out pops f, which is to say that dy star dz is f, which is to say what? It's a solution. So that's why we're doing this Picard iteration from the start, is we knew that if we differentiate with respect to the, if we set up an integral with a variable bound, basically, right? And if we differentiate the integral with respect to the variable bound, it just evaluates the integrand at that variable bound. And that's why the whole iteration should have always been a reasonable one to do, because we should expect that it gives us a solution for the usual calculus 1 reason. That extends to be true here in the context of the algebra. And then I have a solution down here that shows that the solution is in fact unique. I will not. We have suffered enough. But the uniqueness proof is, it's not that hard, but it's, yeah. All right, anyway, so once we know that, enough analysis for one day, right? Once you know that, then other theorems that we would like for A-ODEs follow easily. For example, if we have this differentiation in kth order differentiation operator, where d is like ddz for z an algebra variable, if the coefficients are a-differentiable on a compact star-shaped domain I, all right, and if I also have that g is a-differentiable on I, if I look at the kth order A-ODE, L of y equals to g, with initial conditions, right, I need to give n initial conditions, one for the n minus 1th, all the way down to the first, the 0th, right? Well, then that has a unique solution on I. And the way to prove that is by reduction of order, just like in the usual case. So you just introduce variables, w1 through wk, w1 being y, w2 being y prime, and so forth, and that converts this kth order problem into a system of first order problems, right? Where the, usually most of the first order problems are just like this, dwj dz is wj plus 1, right? That corresponds to, like, when you look at the matrix of the system, it corresponds to that, like, super diagonal of ones or whatever in it, But then the last row is interesting because it shows you how you differentiate the kth thing. This tells us how we differentiate wk. So like wk prime would be this, which would be that. So when you write all this out, you can see the matrix for this system, if we can define a matrix for systems of A-ODEs, and I think we can, by the usual rule, usual song and dance. So what I've got is I've got dw dz equals to aw plus b, where my coefficient matrix has this, the usual reduction of, order matrix. And here's my inhomogeneous term. Got that g down there. So in this context, my f vector, right, I'm feeding it zw, all right? What is the formula? Well, the formula is aw plus b. The question is, does that satisfy the conditions of the existence and uniqueness theorem? What do we need? We need that partial f, partial, in this case, my current notation w, is bounded for each choice of w, for 1 through k. But what are those? what is? That's really nothing more than, components of the matrix or something like that, right? I think actually it's columns of the matrix is what partial f, partial w is, right? So provided that these functions down here are what? A-differentiable in a compact domain, that means they're continuous on a compact domain, which means they can be bounded. And consequently, those partial derivatives can also be bounded, which means we can apply the existence and uniqueness theorem and so find a unique solution to the kth order A-ODE. And so that's why I knew that there should be a unique solution to the non-degenerate kth order A-ODE. What's the trouble with degenerate in this construction? How does that break down? I mean, I assume here that the L that we're decomposing has the form d to the k plus lower order stuff, right? The degenerate case is when there's some kind of zero divisor out in front of the leading coefficient that messes with things. If we had that zero divisor there, I don't think, I'm trying to think what would happen in terms of this. Something breaks down in this argument, right? That's actually a pretty good homework problem. If you guys could explain to me what breaks down in this argument in the case of a degenerate ODE, that would be useful to me. And it probably wouldn't be hard for you guys either. So there's a question for you. This is theorem, well, it's page 11. Theorem 3.3. So not just, I mean, I know the entry level observation is theorem 3.3 does not apply because the degenerate ODE does not fit the form of this. That's not the answer I'm looking for. What I want to know is what it is about it being degenerate makes this construction fail. Is it that we can't bound the derivatives? Or is it something else? Like, what is it that gets in the way of us applying the existence and uniqueness theorem? Because we know something bad happens to it, because I showed you examples last time where we took we had a degenerate second order problem, and we found pretty easily solutions. We found the general solution, and we could clearly identify initial data that we could not fit. Right? So there's obviously there's initial value problems which don't have solutions. And on the other hand, the theorem I'm about to show you, which is the existence of a fundamental solution set, that there are n linearly independent over the algebra solutions, that was torn down by our other example, right? Like 1 plus j times dw dz. If we just do 1 minus j times h of z, any hyperbolic differentiable function solves that 1 plus j times dw dz equation. The solution set's infinite. It's a first order problem. This is very embarrassing from the perspective of the next theorem, right? So I am curious what breaks down in these arguments. I don't know if I've ever really thought about it from that. Just talking to you guys made me think about this question. It's something I should think about. Another thing here. So definition, if we have a connected subset of A, I don't know if I really need that, but there must be a reason I put that there. Suppose we have functions on that connected subset to A. I say the set of functions, f1 through fm, are linearly independent on I if and only if for any choice of m constants, algebra constants, notice, A constants, then that linear combination set equal to 0 implies that all of the coefficients are vanishing. Right. Conversely, if these are not linearly independent, then they're said to be linearly dependent on I. But as we've seen, that does not mean, right, that you can write one as a linear combination of the others. What it might mean is that you can find zero divisors so that multiplying these functions by zero divisors in such a way that they conspire to cancel out and give 0 in some sort of non-trivial zero divisor laden combination, as we've seen that, like with the JZ in one example, right? We couldn't actually express the one function as a linear combination of the other. What we could do was express linear dependencies amongst them. But since we're not working over a field, we can't just solve for any non-zero thing. So how else could I characterize that linear independence in terms of like module theory? Do you remember? What should we say? I think it's linear independence with respect to the A module, but No,
Like,
it's okay. Just the notion of linear independence. I mean, it's
oh, in general model,
yeah. Like what? How's that?
it's just the same form as the above one. Like you allow also zero revisors. I mean, if there is like,
Oh, yeah. I didn't say that. The constants could be anything. Yeah, in the algebra.
so it's the same form,
Okay.
but there's no actual formula to be.
I'm just asking. I'm asking a much less exciting question. Like I'm saying, what would we call it? I mean, it's. I will just label it linear independence with respect to the algebra. You know, we talk about linear independence with respect to the reals, linear independence with respect to the complexes.
I guess we call it A.
A linear independence, yeah, I guess for lack of a better. Through, the Wronskian is surprisingly durable. It works here in pretty much the same way it does in the usual theory. And not only that, it lifts its weight. I mean, it carries its weight too. There's something that happens with the Wronskian which allows me to prove a usual theorem. I mean, Abel's formula still goes through. Anyway, so we define the Wronskian of m functions by the usual determinant. You know, if we have linear independence of the functions for all z, then you can differentiate it and differentiate it and differentiate it and differentiate it, and that gives you that stack of equations and the differential consequences of your original equation. But only the zero solution exists, right? So that gives you this matrix of functions that should be invertible if 0 is the only solution to that, right? So for the usual arguments, if the Wronskian's non-zero, but see, that's not quite right. Now it becomes, if we study linear algebra over module, non-zero Wronskian isn't good enough. We need the Wronskian to be a unit in order to assure that the homogeneous equation has only the zero solution. We need the determinant is actually a unit. So there's a slight wrinkle in the usual Wronskian story as it relates to linear independence. The way that the Wronskian relates to linear dependence for solution sets is more subtle.